Hey guys, hopefully you watched the why we can't make a perfect engine video. Kind of give you a little bit of background about heat engines. But I'm just going to kind of talk through just this one section here. So according to the second law of thermodynamics, no heat engine can convert all heat input into mechanical energy. Okay, so remember, mechanical energy is moving things, moving parts, maybe I should say. Okay, so that's like, in a heat engine, maybe like the one in your car, the moving parts would be initially the cylinders, and then the axles, and then the wheels, and then your car's moving, right? And we have heat input from the combustion of the gasoline, and so we're trying to take that heat and turn it into motion. Okay, but it's not perfect. Okay, so heat engine is anything that tries this, and they have success, right? We can take that heat and use it to move stuff, but it takes some waste, right? There is some waste involved here. Okay, so big ideas here. And again, I really hope you watched that Edpuzzle before you're trying this. But remember, heat always flows from high to low, okay? Unless we have work added. But in this scenario, we are not having work added. We're just having heat flow from high to low, okay? And so the engine kind of works. Heat flows from a heat reservoir into the machine, and then it this is why okay, it may be actually easier to go through this 3-step process how they have it here. So heat engine will, number one, first thing, increase its internal energy by absorbing heat from a high temperature reservoir. Okay, so there's some area that is a higher temperature than other areas. Okay, then they're going to use the heat that is brought in to convert that energy to work. Okay, so we're taking in heat, converting the heat to work, and then kind of getting rid of extra heat to a cooler area. And then start over. So take in more heat, do more work, kick out the extra heat so that it's cold, and then it can take this in again. And so kind of based on how hot is the hot reservoir and how cold is the cold reservoir, there's different amounts of waste work, or not waste work, waste heat, waste energy, maybe you could say. Okay, so here's kind of, again, where I'm trying to underline key ideas of something that's already a summary, but so be it. So only some of the heat can be transformed into work. The remainder is expelled in the process. I'm going to say wasted or lost. Okay, so this is the energy that was taken in by the heat engine, but then not used to do work. All right. So efficiency is basically just a measure of how much energy is not wasted. Okay. So if it was 100% efficient, that would mean none of the energy is wasted. If it was 80% efficient, that would mean 20% of the energy is kind of wasted. Okay, and so this is assuming everything in the engine is working perfectly. So it's ideal efficiency, but you just subtract the two temperatures, the hot minus the cold, and divide it by the hot, and you're there. Okay, I'm going to add, there's a couple things on the top of the next page, but I'm just going to paraphrase them and put them at the bottom of this page. Must use Kelvin. Okay, we have to use our absolute scale so that 0 actually would mean 0. Doubling actually means double the thermal energy, right? And that's really the main idea. Okay, so again, this is going to be a pretty short day. I just want to go through this math practice. Okay, there's one kind of walkthrough together, and this is only 2 questions. This isn't anything compared to those packets we've done in the last couple chapters. So we have a 25 kilowatt heat engine operates between a 3,200 Kelvin hot reservoir and a 450 Kelvin cold reservoir. What's the engine's Carnot or ideal efficiency? Okay, so, and one thing they don't do in this, in this equation that I think is weird, is they don't have parentheses in their equation. Okay, because to me, I look at the equation and I think I want to make sure and do this first. Okay, if I just do this temperature minus this temperature divided by this temperature all in my calculator at once, it's going to do this division first before the subtraction. So I might even go back to my summary page if you're a person who actually prints these off and throw that parentheses in there. You want to make sure and do the subtraction first. Okay. All right, so I know they have it written out, but let's just follow the equation and do it ourselves. So obviously that's the hot one, and that's the cold one. The power of the engine doesn't even actually matter here. Okay, we just take our hot temperature minus our cold temperature divided by our hot temperature. Okay, so again, if I plug this in without parentheses in my calculator, I would get 3,199.9, which doesn't make any sense. Okay, your answer has to be less than 1. Okay, an answer of 1 would be 100% efficient. So any number greater than 1 makes no sense. Okay, it's saying not only did I convert all of my energy into useful work, I magically created more energy for useful work, which we know doesn't make any sense. So we go back and we make sure and put in parentheses around the subtraction part of the equation, and then we get 0.86, which I would probably write as 86% efficient. All right, so I think you have everything you need to know to answer these two. I would just say asterisk, star, clue, reminder, always use Kelvin. Okay, so make sure before you calculate those that you convert into Kelvin. Okay, I'm going to go ahead and retype these on a Google Doc so you don't have to like try to pull that document that I shared the other day up, but I just thought I'd kind of show you where I'm getting these from, and here's my reminder, always use Kelvin. So just these two questions for today, and I think that'll be fine.